This is part 5 of the chemical changes topic on GCSE AQA chemistry. It's valid for dual award and triple award students. And in this video, we are going to move on from what we saw in the previous one and look at a different method of salt preparation. There's also going to be an opportunity to revisit a topic that came up very early on in the course, where we'll be looking at chemical formulae for ionic compounds. So, in terms of what we're looking at here, we're going to see what happens when we add an acid to an insoluble base. Now, in simple terms, what we're talking about here are metal oxides. So there's a required practical that goes with this. I'll very quickly talk through. There's a big similarity to the practical that we saw with the metal and acid in the previous video. You take a measured volume of acid, you put it in a beaker and you warm it. Now you might be thinking about why we're warming it. That's so that the reaction will take place quicker when we add our metal oxide to it. So we heat gently, we add copper oxide, and the copper oxide is a black powder. But when we add it, we are going to make some observations, and we'll talk about what those are in the questions that follow. You carry on adding copper oxide until the reaction stops, until it's in excess. And then you're going to filter to get rid of the excess copper oxide, and you're then going to gently evaporate your solution to get your salt crystals in the end. So you do need to be familiar with the methodology of this practical. You need to be able to recall the steps and understand why we're taking them. Let's have a look at some of the questions that go with this. What do you first observe when the copper oxide was added to the acid? Well, the first thing that you see is that when the black powder gets added, the solution changes colour. We actually get a blue solution forming of copper sulfate. We are still going to have copper oxide visible. A black powder will be present because it doesn't react instantaneously. So you'll see both of those things. What did we observe when the excess copper 2 oxide was added? So until we'd added more than was needed for all of the acid to react. Well, at that point, the black solid will start to fall and settle at the bottom of the beaker. It remains as a residue because it can only react if there is acid there to react with. And what did we observe when the salt was left to crystallise? Well, the blue solution is gently heated and we're left with blue crystals forming in the evaporating basin. The blue crystals are the copper sulfate crystals that we would expect to see here. Couple more questions. And in terms of the word equation, well, we take our metal oxide, our acid, so it's copper oxide and sulfuric acid. We make our salt. We talked a lot about where salt names come from on the previous video. Sulfuric makes sulfates. With a metal and an acid, the metal goes at the start of the salt name. With a metal oxide, it's still the metal that goes at the start of the salt name. The big difference here is that we're making water, not hydrogen, as the second product. And you will need to remember that. In terms of the symbol equation, well, copper 2 oxide is CuO. Sulfuric acid, you need to know, is H2SO4. You would need to work out the formula of copper sulfate as CuSO4. And obviously you need to know that water is H2O. I've put the state symbols in and you will notice the H2O is liquid. It's not aqueous because aqueous means dissolved in water. Water does not dissolve in water, so we put L. Couple more questions. So the general equation, a metal oxide and an acid make a salt and water. And if you remember that, you're well on the way to being able to complete a successful equation. In terms of the diagram, I'm not going to redraw the diagram. I'm going to show it on here, and I'm going to say that this is not actually ideal for what you might draw. It's probably a little too complicated. You wouldn't draw the Bunsen burner, for example, and you certainly wouldn't draw width on the tripods. The key things that we are looking for here is that the diagram is cross-sectional, that it's two-dimensional, and that it's fully labelled. So the two-dimensional, the minute you go into 3D, you're going to start to lose marks, and cross-sectional means you've got to imagine you have sliced the apparatus down the middle so that you can see exactly what's going on at the heart of it. That means that if there is, for example, a delivery tube going into water, the water would not cross that delivery tube. There's more examples of that in other videos. I'm just going to remind you here of the key details. So we're going to finish off this video by looking at some common ionic compounds and working out their formula. And a reminder, you need to learn what's in this table. You are going to have to know it for the exam. So let's try and put them in place. I'm going to use the Seesaw method. There are different methods out there that you can use. So sodium chloride is sodium and chlorine. I draw my seesaw with a positive ion on the left, the negative on the right. I then put the charges on top of the seesaw. I want my seesaw to balance to 0. And what I can see here is I've got a +1 and a -1. That comes to 0. So the formula is NaCl. Let's look at a different one. Let's look at calcium chloride. Calcium chloride, draw out my seesaw again. Positive left, negative right. Here, calcium is +2. Chloride is only -1. If I'm going to balance this seesaw, I need another -1 on the right. That means I've got 1 calcium and 2 chlorines. That means that calcium chloride is CaCl2. And then ammonium sulfate, a little bit trickier. An ammonium ion is NH4, you need to know that. A sulfate ion is SO4, you need to know that. You also need to know that ammonium has a +1 charge and sulfate a -2 charge. Once you've got those facts, you can balance the seesaw just as we did previously. I have another +1 on that side. So I've got 2 NH4s and 1 SO4, but I can't write it the way that you see it on screen because this looks like NH42 SO4. If you have multiples of a complex ion, you put them in brackets. So we're looking for the formula that you can see here. On to the next one. Copper 1 chloride. You have got to remember with transition metals, the Roman numeral tells us the positive charge on the metal that precedes it. So copper and chlorine, I have +1 and chloride is -1 because it's in group 7. I don't need to do any more balancing on the seesaw. I need 1 of each, so it's CuCl. But if I do copper 2 chloride and I draw out my seesaw identical to above, but this time my copper is +2 and my chloride is -1, I need another chloride to balance that seesaw. So I've got 1 copper, 2 chlorides. Formula of copper 2 chloride is CuCl2. Now let's take a look at aluminium sulfate. Now, aluminium is in group 3, so it's +3. You have to know that sulfate is -2. And I'm going here for the lowest common denominator of charges. What's the lowest number that will balance out my pluses and minuses? Well, it's 6. 2 + 3s and 3 - 2s. That means I need 2 aluminium ions and 3 sulfate ions. So I write it out, Al2, SO4, 3, but because this is a complex ion, I need brackets around the SO4. Let's look at the next one. So I draw out my seesaw. Aluminium is in group 3, bromine is in group 7, so that's +3 and -1 respectively. To balance out my seesaw, I need 3 of the Br minuses, so my formula is AlBr3. And then for the next one, I have NH4 and I have NO3. Now, NH4, ammonium, is a +1 ion and a nitrate ion, NO3, is a minus ion. Again, facts you have to remember. But I don't need to do any more balancing. So my formula is an NH4 followed by an NO3, NH4, NO3. Don't be tempted to combine the ends. Keep the complex ions separate. Couple more examples here. Let's go for potassium sulfate. K is +1. Sulfate is -2. So I need 2 of the +1s to balance my seesaw to 0. So my formula is K2SO4. And the final one, a simple one to finish off. Na and I. Na is group 1, +1. I is group 7, -1. I need 1 of each of them. My formula is NaI. That takes us to the end of this video. Thank you for listening and goodbye.